Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on the 24th of June, 2025, T 20 hours, 23 minutes, and 39 seconds, .000Z. This paper, published just last week, details how a robot controlled by a large language model achieved a 43.3% win rate in a board game tournament. The paper is titled ARC, an open-source Python-based framework for robot learning, and its goal is to make building robots as straightforward as training an AI model. It introduces a new software framework that bridges the difficult, low-level world of robotics programming with the flexible, Python-centric tools common in machine learning. Alright, so this figure really shows the core of their approach. At the center is the ARC node network, which is like the system's brain. It connects different components using what they call action channels for robot commands and observation channels for sensor data. The key innovation here is how this network can control either a physical robot or a digital twin in a simulator. A simple switch in the configuration file toggles between them without changing any other code. This seamless sim to real transition is what makes the framework so powerful for researchers. Building on that idea of a seamless sim to real transition, this next figure gives us a perfect visual. At the bottom, we see two scenes. On the left, a physical robot arm, and on the right, its digital twin in a simulation. The amazing part is shown in the code snippets above. The policy, which is essentially the AI's set of rules for making decisions, is identical for both scenarios. Researchers can develop and test entirely in the simulation, then deploy that same code to the physical robot, just by flipping a single switch. So how do you create that decision-making policy in the first place? Well, this diagram shows their streamlined process for imitation learning, which is basically teaching the robot by showing it examples. On the left, you can see various ways to demonstrate a task, like guiding the arm by hand or using VR. This demonstration data is captured using a tool called LCM Logger. LCM, or Lightweight Communications and Marshalling, is a system for fast communication between software components. The data is then processed, used to train the policy, and finally deployed to the robot. And here we see that deployed policy in action. These images show an OpenPyro humanoid robot executing two different tasks it learned through that imitation process. In the top row, it's carefully flattening a shirt, and in the bottom row, it's picking up a banana and placing it into a bowl. Both of these are guided by what's called an action chunking with transformers, or ACT, policy. This is a powerful type of AI model that learns to string together precise actions, demonstrating the framework's ability to handle complex, contact-rich behaviors. Okay, so the framework isn't just for robot arms. This figure shows its capabilities for mobile robotics. On the left, we see a husky robot in a simulated kitchen. Then, in the middle, it builds an occupancy map, which is just a 2D floor plan, using a technique called SLAM. SLAM, or simultaneous localization and mapping, is how a robot builds a map while tracking its own location. Finally, on the right, it uses the A-star search algorithm, a classic pathfinding method, to plot a course. This shows the entire end-to-end navigation workflow is handled by ARC. So having seen what ARC can do, this table puts it all in context by comparing it to other frameworks. You can see ARC at the top and alternatives like ROS2, a common but often complex robotics standard, listed below. The columns are all desirable features, from Python support to that seamless sim to real transition. What's striking is that ARC is the only one that checks every single positive box. It provides a complete, modern toolset, avoiding the limitations you see in other systems, like a lack of built-in learning tools or limited hardware support. So as that comparison makes clear, the ARC framework really stands out. The core takeaway here is how it bridges the gap between traditional, complex robotic software and the fast-moving world of modern AI by providing a unified, Python-first toolkit with that incredible sim-to-real capability. It drastically lowers the barrier for researchers. It supports advanced methods like diffusion policy, which is a powerful way for the AI to learn smooth, effective actions by studying examples. Ultimately, it's a catalyst for progress. That's all for this episode. Thanks for listening.